Today I want to talk about Traffic Turk, which is an application we've been working on here at Illinois to monitor traffic during extreme congestion events. Okay, so most of the talk is going to be focused on sort of linking together transportation and mobile computing, and I want to kind of give a big picture overview of sort of why that's happening and some of the different things that people are working on broadly in the field and then also specific to this project. So to kind of set the stage, I want to just first introduce you a little bit to some of the challenges that the transportation community has identified for transportation. So obviously, if you've ever been through Chicago, you know congestion is a major issue. Accessibility, equity, these are becoming very important. Energy efficiency and the environment. These are sort of like the grand challenge problems in transportation. And if you look at how we've addressed these problems in the past 50 years, it's been mostly focused on building infrastructure. If you look at how we'll address these problems in the next 50 years, it's going to be more and more focused on integrating technology with the infrastructure. And when you start trying to do technology and infrastructure, that creates one huge problem. And that really has to do with the timescales at which infrastructure systems evolve. Okay, so if you go back to 2007 and look at the best-selling mobile phone, I doubt that anybody in this audience has a Nokia 1200 device. But if you look at the best-selling car, probably 2 or 3 of you in this room may still drive a Toyota Camry from a decade ago, right? And the biggest piece of infrastructure was the big dig, okay? And the lifespan of an infrastructure project is 45 to 100 years. I mean, the joke within the civil engineering community is that we say we build the infrastructure for 2060 today, right? So if you're going to try to disrupt this infrastructure, doing that with technology is going to be very difficult because the technology has to last for so long, right? And the technology evolves so quickly that by the time you get it deployed everywhere, it's going to be obsolete. And there's obviously a lot of work happening right now in vehicles where people are trying to make the cars smarter, but even that takes 10 to 15 years before that technology can be pervasive out in the field. But then if you look at the mobile phone, this is something that everybody's carrying with them in their vehicles, and it's something that's personal. And so that's really allowing us, for the first time, to build transportation systems that are human-centric instead of infrastructure-centric. And so a lot of the disruption right now in transportation is happening in the mobile space. And part of the reason for that is just because cell phones are the biggest sensor network on the planet. You know, there's more than 6 billion devices out there, and like I said, they are on the person. So we can actually, for the first time, start to understand how people and infrastructure interact, not just looking at how the infrastructure randomly senses things in its environment. And so people are looking at this and saying, okay, well, it comes on with sensing and computing, and this just gives us a chance to sense infrastructure in ways that were previously impossible beforehand. And to give you some ideas of some of the applications where this has really started to emerge, who here is familiar with Uber? A few people. Uber is a company that's very disruptive right now. What they built was a smartphone application that allows you to basically reserve a taxi. It started with the black cars, and now they've moved into sort of the private driver space where you can, with a clean driving record and this app in your car, start giving rides to other people just like a taxi would. And it's disruptive in quotes there because they're getting lots and lots of lawsuits from the Taxi and Limousine Commission saying, this is unfair competition, it's not regulated, things like that. But if you look in Chicago, New York, Washington, D.C., in San Francisco, a huge fraction of rides are starting to come from services like Uber just because they provide an app where you can actually see where your taxi is. And you can see the taxi coming to you and not wonder, is this person actually coming to pick me up or not? The phone also deals with all the billing, so you don't even have to tip the driver. It's already taken care of. Okay, Lyft is a very similar service. Waze you may be familiar with was recently purchased by Google. This was sort of a social driving application. They originally started off as a mapping application. It seems almost crazy, but building maps is actually a very hard problem, as Apple demonstrated. Waze got around this problem by literally paying people, incentivizing them with virtual cupcakes and virtual tokens to go take routes other than the route that they had originally intended to, so that they could verify that in fact a particular path is routable. And they started off in Israel, and they built, in fact, very quickly some of the best maps in Israel, then moved into the United States. They've got a very active user base. They keep them engaged with some gaming, and they're actually influencing driver behavior by encouraging people to take routes to get more points and sharing that information with other people. Smart Trek is an app that's been recently developed in Arizona. They're actually looking at trying to change the times at which drivers leave so that we can actually kind of schedule the demand on the transportation infrastructure. If I can encourage you to leave an hour before the rush hour, you may get to work much quicker. And so that app is really just designed to show you how much time you could save if you were willing to leave at a different time instead of take a different route. So that gives you some just big picture overview of how mobile phones are already starting to build smarter transportation systems. For the rest of this talk, I want to focus on one very specific application of smartphones in traffic, and that's really crowdsourced traffic, how to use all these devices that are out in the field to monitor traffic. And I want to talk about sort of the state of the art, what companies like Google and Apple and Waze are doing, and then I want to talk about what they can't do, what they're really struggling today with monitoring traffic. And that's really why we invented another application called Traffic Turk. There are a lot of apps already in traffic monitoring. Ours solves a very specific problem, and that's trying to understand traffic during events. And I'll try to highlight why event-based traffic is much, much harder for companies like Google to monitor than typical day-to-day traffic. And so I'll talk about some of the application development, how the app works, and also talk about some of the experiments that we've done here in Illinois and also in New York. And then I'll talk a little bit about behind the scenes, sort of how we make the app work. What are some of the data processing challenges that happen? You know, the app is really just the front end for us as researchers. We're trying to get data in to our systems. We're trying to process that data, make some sense out of that data, and then feed it back to users so they can actually take action based on this information. So I want to just give a little primer in terms of how people used to monitor traffic and sort of what the transportation view of traffic monitoring has historically been. It's obvious that traffic congestion is a major problem. There's more than 4.2 billion hours of delay in the United States alone caused just by traffic congestion. And the way that we've typically gone out and monitored traffic, we had sensors that went directly on the roadway. So either you put coils in the road and as you drive over them you can count the vehicles, or you have little wireless sensors that basically do the same thing. They count the number of cars that are crossing over that. The problem with these types of sensors is that if you ever do repair work on the road, you destroy the sensor. If you ever have the sensor break, you have to shut down the traffic. So pretty quickly people said, well, maybe it'd be better if we got off of the roadway and just put the sensors on the side of the road. So that introduced sensors like video cameras and side-fire radar detectors that are on the side of the road, aimed at the road, can process the data very quickly, measure again the speed that vehicles are moving and also the flow, how many cars are passing at a point. And then recently, people have started looking at using sensors inside the vehicles themselves. As the cost of sending data over the cell phone network has dropped, as the cost of GPS has plummeted since it became widely available on every mobile device, it's become possible to actually start looking at the vehicles themselves as sources of data. And when that happened, it really started to change who cared about traffic. Instead of transportation agencies having the most reliable traffic information, it became the firms that had the most GPS data that had the most reliable traffic. So INRIX is a major company that was spun off of Microsoft Research. They buy GPS data from a bunch of providers all over the country, from phones, from fleet vehicles, process that and turn that back into traffic information. Traffic.com, which became Navtech, which became Nokia, which became here, based out of Chicago. They also have a traffic product that is very similar. They buy data from anything with a GPS in it. It's increasingly becoming GPS smartphones for all these companies. And then companies like Google got involved as well. So there's a lot of action right now with the companies trying to acquire these huge streams of data, try to make some sense out of it, and format that back in a framework that they can sell to people to help give them better traffic guidance. But I think there's one other thing that mobile computing is actually doing for the transportation systems. I claim that this is just the fundamentally wrong way to look at traffic on a map. I mean, if we go on to our mobile devices, this is very similar to what we see just formatted for the phone, right? And why is this so problematic? Well, if you think about it, you're showing tremendous information about roads that you can't actually drive on. By the time you get to any of those spots in Chicago, you will have already taken some time to get there, and the traffic conditions will have changed. What you really care about is sort of point-to-point routing. You know, you want, when you open up your app, you don't want traffic information. You want a destination, an origin, a path to get there, and one that's going to be reliable. Okay, so I think you'll see over the next 5 to 10 years that transition a lot as more and more devices inside the vehicles become better suited to giving people information as they're driving. We all do this on our drive now, holding our phones and kind of trying to listen to Google tell us what to do, but practically that's not a very safe way to have that information streamed into the vehicles. The car manufacturers are working very hard on trying to figure out interfaces that can give us that content in ways that aren't disruptive to our drives. But I think you'll never see this type of information shown in a vehicle that comes out 10 years from now. So I want to talk a little bit about some work that I've done in the past that really sort of set the foundations for how you do monitoring with GPS devices such as smartphones. I was part of a team at UC Berkeley along with Nokia, Navtech, and the US Department of Transportation to look at what the possibility of using GPS data from smartphones would be for monitoring traffic back in 2008. And at this time, again, there were relatively few smartphones available. This was, I think, right around the time the first iPhone came out, which did not have GPS. It did not have 3G. It had a very low quality camera on it. And yet it was clear that the mobile phone space evolved so quickly that we need to understand what type of potential these devices would have. So what we literally did is we seeded a roadway in California. This is the San Francisco Bay Area. There's about a 10-mile stretch of roadway, and we hired a team of graduate students. I think we had about 165 graduate students that just drove that stretch of freeway up and down for 10 hours one morning. And they made up something like 2 to 3% of all the vehicles that were on the road. We gave them all cell phones, and those cell phones were sending GPS data back to our servers in real time. We could process that data and then measure what the traffic conditions look like. Of course, the logistics of an experiment like this are very involved. We had to rent 100 vehicles for insurance purposes. We had a team of 75 people in the background that were just tracking all the back-end systems, but also all the assets. And you start to think about it, if you give somebody $1,000 cell phone at the time, a rental car, and $200 cash, and you're not that far from the beach, there's a good incentive for you to start taking a little bit of a sidetrack. And so one of the things that I'm not going to talk much about in this talk, but what was really important in this work, we not only looked at how you could use this GPS data to monitor traffic, we also looked at it from how do you make sure that this GPS data that you're collecting can't also be used to identify other properties of the driver. And I think from what you've seen in the news recently, privacy in mobile computing is becoming a first-class priority. And what we looked at is making sure that when we collect this GPS data, you want to make sure that not only is your name removed from your trajectory of your GPS data, but also split it up in a way that it's not possible to re-identify who you were. So removing your name from the trajectory, we call that pseudo-anonymous data. And the reason I use the word pseudo-anonymous is because it's only anonymous until you overlay that on a map. Pretty quickly, it's easy to see that you left from your home and you went to your work. And even though I don't know your name yet, it's not very difficult to recover who you are. And so that's the type of thinking that we had in this project, is to say, okay, let's figure out a fundamentally new way to collect the GPS data so that we can't sort of re-identify who the user is with other statistical algorithms to do this inference. And so basically the main kind of idea behind that is rather than sending all the data as a unit, here's the trajectory, we would have markers on the roadway where the vehicle could or could not possibly send data. Okay, and by having the data come in to a spatial sensor, it allowed us to basically guarantee that if we put the sensors far enough apart, we can't identify that the measurement that came from this sensor is the same vehicle that sent me this measurement from this sensor. So it allowed us to deconstruct that path. Okay, well, you destroy the quality of the information. The question is then how do you reprocess it in a way that you can make some sense out of it? So just to give you an idea, I mean, this is what the traffic conditions look like. This is time on the x-axis and space on the y-axis. The vehicles are driving up this way. It's color-coded so that the blue is very fast-moving traffic and the red is very slow. You can see this huge amount of congestion that was caused very early in the morning was actually due to an accident. And so this project really demonstrated the fact that by having so much GPS data available, you could actually very quickly even identify the fact that there's major disruptions that wouldn't be captured by any sort of historical algorithm. You really need the data. Of course, that put a lot of pressure on us because at 10 o'clock in the morning, we're expecting free-flowing traffic. If anybody's done any demos, you know that the one thing that you're afraid of is sort of a corner case, and that was the first thing we got. But we managed to actually produce meaningful traffic estimates, and that sort of gave us proof of concept that we were doing the right stuff. And so I mentioned some of those sensors that exist on the roadways. That's a speed contour of what those types of sensors look like. And you can see that qualitatively, I mean, we get the main features very similar. The main congestion. This is in the afternoon again, where the congestion recurs. So how do you know if it's any good? How do you validate this stuff? So what we did is actually took some video cameras and had a team full of undergraduates actually do license plate recognition manually. Okay, and they would actually write down the license plates. We had them set on 2 different bridges, and we'd measure the travel times of those vehicles as they went from one bridge to the next. So we'd actually have some travel times of the vehicles that weren't part of the experiment sending us GPS data. And we take all this data, reconstruct it, produce the travel times, and we see, were we actually able to compute travel times with any reliability. And so by now everybody's sort of familiar with the Google traffic type maps. This is sort of a recolored output of our traffic estimation algorithms. The traffic we're looking at is going to be moving in the northbound direction. These 2 plots, what I'm going to show on the top plot is the video detection, the travel times we got off of this license plate recognition. Every sort of crosshair, this pink crosshair, is an individual vehicle that's been re-identified. The blue line is a moving average plus minus a couple minutes to sort of smooth out the data. And in the bottom here we have in the green, this is the plus minus a few standard deviations of the model output. Our estimation algorithm not only gives you the traffic conditions, but how much uncertainty there is on it. And you can see in that morning accident, actually, we missed it the very peak of the accident because we actually had relatively few vehicles on the road. We had just started the experiment. But very quickly, we start to track what the traffic conditions look like, and we actually get the clearing of that incident very well identified. You can see that that'd be really helpful later for routing algorithms. You can tell somebody to stay on the freeway until the last possible moment because the accident has cleared enough that you can actually get to that last exit ramp. And that's going to be a faster path than waiting to get off at an earlier exit ramp, knowing that the congestion might already be causing you to sit and you might not be able to get to that next exit ramp. So as the estimate continues to evolve, you see sort of the peak from the lunch crowd. It's a Friday afternoon, so people start leaving home anywhere between 3 and 5 o'clock in the evening. And again, we're able to track not only what the traffic conditions look like, but also how uncertain we are on that. I'm not going to talk much about the estimation techniques that we use, but it's some variant of Kalman filtering on a traffic flow model that we use to produce that. If it doesn't make sense to you, it's a black box that turns the data into something useful. Okay, so that kind of shows you how promising using mobile generated data streams would be for measuring traffic and for also giving people real-time information that they can make decisions on. What do the companies like Google and Apple struggle with today? It's really event-based traffic and it's surface street traffic. The surface streets are hard because there's just so many more roads. Okay? That's the first challenge. Many, many more roads than there are on the highways. Number 2, the number of vehicles that are driving on those roads is much lower. Okay? And number 3, it's a different type of people who use the roads, the surface streets compared to the highways. Okay, how many people drove to work today with a navigation device on? Nobody. Okay, so on your phone, you know that the GPS is a very power-intensive sensor. It uses a lot of energy. Google and Apple don't turn the GPS on while it thinks you might be driving in the background without you having maps on. They want to make sure that if you're using your battery up, that you're using it for something that actually matters to them. So the only time Google and Apple are getting GPS data that they can make some sense of the traffic conditions on are when you're running navigation. Now you see the problem. If you're not navigating to and from work, most of the drives on the surface streets, you're not actually getting any data from. Okay, so then you have to augment it with fleet vehicles or with in-vehicle GPS units, and those just aren't as widespread today as the cell phones are. So it's coming for sure, but today they really do struggle with the surface street traffic monitoring. And moreover, there's one other piece that makes it harder, and that's the fact that there's traffic lights there. And they don't have knowledge of even where the traffic lights are, let alone how they operate. So it just fundamentally changes how reliable the information they can give you because they don't know if you're going to get stuck at a traffic light or not. Okay, so it's just a much harder estimation problem. So what they do instead is they get this data collected over several months or years that they've been running these services, and they try to build statistical models of what typical traffic conditions look like. Okay? And then when they get new data coming in, they try to say, well, how can I correct my historical information based on what I'm seeing now to give a prediction which is based heavily off of what I've seen in the past, but also what I'm seeing right now. They kind of combine the historic information with the real-time information. But when you don't have much real-time information, it means you have to be pretty heavily based on what's happened in the past. Okay? This creates the huge problem for events because you haven't seen them in the past. You don't have historical data that shows you what typical traffic conditions look like. So that's really sort of the motivation for building a different way to collect traffic data, again using smartphones, but in a way that we can quickly deploy some sensors out in the field and that we can get the information on the surface streets during these events. Okay, so in particular we've been looking at what I've sort of called extreme congestion events. They're special events that generate huge amounts of traffic. It could be something like a sporting event, like a football game, the Super Bowl's coming up, a NASCAR race, or it could be something like a natural disaster. We sent a team actually out to New York right after Hurricane Sandy. I can assure you that during Hurricane Sandy you had huge disruptions. You had traffic lights that were out. There were no traffic signals running. That changes the traffic patterns. People were trying to evacuate the city because they were worried that parts of it were going to flood. That changes the traffic patterns. The taxis ran out of gas. They had to go to another state to get fuel. That changes traffic patterns. All these things basically tell you again that your historical data is going to be effectively useless at trying to predict what's happening right now in the field. So instead you need some other way to collect the traffic data. And that's sort of what the inspiration for Traffic Turk was. We said, okay, well, how can we quickly collect this data? We're going to do it with smartphones. We're going to do it in a very strange way, the very manual, mechanical way. Okay, literally what we're going to do is we're going to send people out into the streets and they're going to stand at an intersection, and every time a car drives by, they're going to swipe their finger to record that a vehicle has passed. So for example, see the car coming here and turn right, swipe your finger down. See it go through, swipe that way. See one coming the other way, swipe it this way. Okay? Well, how did we come up with this idea? It turns out, I mean, it's kind of embedded in the name. How many people are familiar with the Mechanical Turk? Quite a few people, but for those of you who are not, the Mechanical Turk actually started off as a mechanical chess-playing machine. Okay? And this machine in the 18th century went around the world and beat a bunch of famous chess players. The question was like, how did you do it? I mean, there was no computing at the time. What they did is they put a great chess player inside a box underneath the table, and that guy moved the levers, right? Okay, well, the box is as good as the chess player inside it is, right? And then Amazon went ahead and, inspired by the same thing, introduced a web service called Amazon Mechanical Turk. And for jobs that are really easy for humans but really hard for computers, you upload these jobs to Amazon Mechanical Turk, for example, identifying images, identifying the difference between, I don't know, a horse and a cat. If you don't have a machine learning algorithm that's already done it, you need to seed the algorithm. You upload it to Mechanical Turk. It ships it out across the world for people who, per picture, for a few cents, will tell you whether it's a picture of a horse or a cat. Okay? But it gets done very quickly, just like any other distributed web service. Well, transportation has its own Mechanical Turk as well. In fact, this was my first job in civil engineering. I took one of these boards. It's called a turning movement counter. Took one of these boards out to an intersection, and you literally stand there and you press a button every time a vehicle goes through the intersection. And why do they do that? They use that because we have so little sensors on the road. What we want to do is update the traffic lights to make sure that we're getting all the vehicles through there. If the traffic patterns change, over a couple years, we need to go back and readjust the traffic signal. The way that we do that is we go out, take one of these boards, get the new traffic conditions, take that back to our office, plug it into the computer, run an optimization algorithm, go walk back out to the signal, and put in the new timing into it. So we said, well, the reason that this is very ineffective is that those boards are several $100s, right? And they have no communication capabilities in them. But if we could make that on a phone, then we could have people go out. If you've got a phone, you can be part of my team. We go out and put you at every single intersection in the city. You start swiping your fingers away, and all of a sudden now we have very, very rich traffic information at every intersection when we need it, and it can be streamed back to us in real time. Of course, there's some challenges with building a smartphone-based turning movement counter. We decided to use Android because I thought, oh, well, that's going to be cheaper. I won't have to pay for any sort of Apple development stuff. Well, some of you may have already seen these pictures, but this is from OpenSignal. It shows all the different screen sizes that might be available. With every change in the screen size and every change in the hand size of a user, swiping becomes a tricky problem. We actually can't use any of the built-in swipe recognition tools because those are typically meant for up, down, left, right, and we've got 12 different swipes that we're trying to detect. And the way that people hold the phone, sometimes they swipe in the middle of the phone, sometimes they swipe on the top of the phone. We really want the direction and not so much where you swipe on the device. So we spent a lot of time actually building good swipe recognition algorithms based on a bunch of manually labeled data, put a support vector machine on it, allows us to get something that's actually very statistically accurate, something like 99.98% of the swipes we can now recognize on the devices. Of course, device fragmentation, again, another challenge for anybody that's developed on Android. You get it to work in the lab, you get it to work on a few devices that you've seen, you go out and throw the thing in the wild, and all of a sudden you see things that you've never seen before. We had our app fail on a phone. The reason it failed was because the user had 72 background processes running. Okay, there was no memory for our app to run, right? But you don't know how to detect these things until you've seen it in practice. So the device fragmentation it's an ongoing challenge for us in terms of making sure that our app not only performs well on the phones that we have, but making sure that it performs well on the rest of the devices. And user interface is also very challenging because, like you, most of our users are not transportation engineers. They have no idea what a turning movement counter is. And in these emergency situations, I need to get you in, trained, and in the field quickly without trying to tell you the full history of transportation systems. So UI design has been very challenging. We participated in a workshop on campus. It's an engineering open house, brings in a lot of students from middle school and high school. That was actually really helpful for my engineers because the students were not reserved in telling us how they felt about certain aspects of the design. You may think it's good, but when you throw it out in the field and people just tell you this UI is terrible, I don't know what I'm doing, they set it down and go on to the next table. So that was actually very helpful in terms of trying to solve some of the orientation challenges we had. So Traffic Turk now, it's on Google Play. It's really kind of a boutique application. It's mostly people in the transportation community that are using it, but if you'd like, you're more than welcome to download it. But I want to kind of show you how it works. So when you open up the application, you get a map. It shows you different intersections that you can count at. You can select one of the intersections, and then you go out to the intersection, and you're faced with a screen like this. Okay? And what this is sort of like the orientation screen. I know where the phone is. I have no idea which way you're facing. And I need to make sure that whatever the physical model of the intersection is, and whatever your mental model of the intersection is, and whatever model the phone has of the intersection, those all have to coincide in order for the data entered by humans to actually mean something to me. So the way that we solve this problem, although you can use the compass and the GPS, that doesn't solve the problem of making sure the mapping from the user to the phone is correct. So we actually broke some of the automation and went back and actually had the users manually label this. So this is in Decatur, Illinois. This is Main Street coming down here and McKinley Avenue going across the screen. And so what you can do is in the app, you just literally drag the Main Street to where you want Main Street to be labeled in the app, and you drag McKinley, McKinley to one of the sides as well, and now the phone knows how you think you're going to be counting the data. Okay? So then once the phones have been labeled, then you enter into a counting screen. And this is actually some data that we use to help train some of our volunteers. This is just shot off of a parking garage in University Avenue, just on North Campus. And literally as soon as you start the traffic, you start counting. So this would be 1, 2, a right turn, another car. And at first, you can play with yourself right now and see how difficult this would be. Initially, it's a little bit intimidating. After you do this for about 3 minutes, it becomes trivial. It becomes like a video game. You don't even look at the device any longer. You just start swiping. And you can actually, surprisingly, there's been some studies done on how accurately humans can do traffic counting at major intersections. It turns out that the humans are about as accurate as the fixed sensors, because the loops, the video cameras, all those have errors as well. So humans make errors too, but the human error is about the same. It's in the order of 97% accuracy on the counts. So it's actually quite reliable. So we do a little bit of training with the users ahead of time before we go to the experiments so that the first 5 minutes of their counting isn't frightening. They've already seen it. So I want to talk a little bit about some of the experimental deployments that we've done. The first major test we did, a lot of times we do these experiments without thinking about just how hard they're going to be to manage and practice. We decided it'd be good to try something around campus. So we waited till the Illinois-Indiana homecoming football game in 2012, and we hired 100 people to go sit at every major intersection in Urbana-Champaign. And we looked at the first 3 hours into the football game, getting the traffic from everybody coming in, and looking citywide what the traffic conditions look like. So this is sort of an animation of the data that we collected. We're starting at the football game, and we'll kind of zoom out, and you can see these white columns that pop up everywhere. These white columns are roughly scaled to how much traffic was flowing through that intersection as a function of time. Okay, so if you've ever been to any of the football games, you know the major routes into the stadium are coming down Neal Avenue and Lincoln Avenue. This is Neal Avenue and Kirby, one of the highest flow intersections in town for these games. What you don't see is this intersection right here, which basically on a non-football game day, it's a stop sign, and it has, I think we went and checked, something like 6 vehicles per hour cross through there on a Saturday morning when there wasn't a game. Several thousand vehicles showed up during the game. So this is, again, proves the point that you would never spend money to put dedicated sensing infrastructure there. Your historical information would never be very helpful. What you really need is sensors on the ground to help make some sense about what's happening. So we actually recruited all the students that participated in this experiment from campus. I'd say incentivize. We pay them $50. There's a trick here, though. We said also get a free pair of smartphone gloves. This is in October. And we're doing the recruiting in September. It's nice and warm. The experiment's in October. It's nice and cold. So we actually had to give people touchscreen gloves so that they could actually still swipe the vehicles in when the weather dropped. But what's that?
Oh, so did not lose a finger.
Yeah, exactly. Well, we learned this firsthand from our own experience going out and counting and realizing that, man, hey, our fingers got very cold. So we trained the students, kind of gave them a big overview of what we're trying to achieve. I think probably the most important thing with kind of having these training sessions, yeah, it helped them become more comfortable with the application, but more importantly, it helped them sort of understand that the reason we need you to participate is because we're trying to do city-scale traffic monitoring. During that event, we were probably the most densely instrumented city for traffic monitoring anywhere in the country. But if you don't show up, we have a huge problem. So this is more to make sure that the users that were being paid, although it sounded great on Wednesday night, Saturday morning at 7 o'clock in the morning when we needed people to actually get out in the field, the bed is also very attractive. So we really try to encourage people to show up. We had the students go out. They sat at, like I said, 100 intersections. They got creative. Some people counted from inside restaurants, other people inside their cars, other people from, you can see, from balconies. But the experiment was very successful. All the data came into our monitoring tool. This is something that we have internally that shows us what the traffic conditions are at each of the different intersections. Also shows us things like the battery life, so we could identify one user showed up to the experiment with her phone charged at 12%. Well, in addition to running the screen the entire time and GPS periodically to make sure you're at the intersection you said you're at, we also run Bluetooth in the background so that we can actually record other vehicles that have Bluetooth headsets in the cars. We can see them go across one intersection, we can see them at another intersection, and we can actually get a travel time between the two intersections. So we're burning a lot of sensors right here, eating up battery. So we told them to charge their phones, and some people didn't. That's why we had a team of people in the background that were helping with everything from making sure that the servers were up and running, the backup servers, if we needed to switch over stuff, we could. And if we needed to send out backup phones or backup volunteers, they could get out in the field and help the people that were counting. And just to sort of say that there's a handful of students that have helped me with this. Everybody in the orange box is one of the students in my lab that's been assisting us with this experiment. So it's a huge effort. This is stuff that you can't necessarily write papers on the first time doing all this development work, but it really enables the research team as a whole to get data that nobody else in the country has access to yet, and allows us to do science that we just can't do anywhere else. So right after that experiment, literally a few days later, we redeployed our entire system in New York and went to Columbia University, recruited students there, and had them do traffic counts in New York City right after Hurricane Sandy. This is a huge, huge challenge. We had never designed this application to be sort of event-based, let's say, natural disaster-based traffic monitoring. We always sort of viewed it as pre-planned events. The natural disasters created a huge new problem, right? One of them, right off the top of my head, it was clear we were going to run into trouble. All that Google Maps overlay only works when you have a connection to the internet. And when the cell phone network goes out, the data is still valuable. You can still use that to understand the impact of the hurricane, but you still have to be able to get users oriented correctly. So we ended up having to rewrite a separate interface that would allow the app to work even if you didn't have a map, where you could basically scroll through a list of intersections to select where you wanted to be. So huge challenges when you start to think about the fact that the UI not only needs to work with perfect data connections, but it also needs to work when there is no data connection. We have the view that you should expect that the user will have a data connection when they install the application, and that's it. And from that, any intersection that's been cached in their phone, they should be able to count at and collect data, and we should eventually get that data if they ever connect to the internet again. That took some rework and a lot of engineering to do, but our current version of the app actually does that quite well. Then the most recent experiment we did this past year was for the Farm Progress Show in Decatur, Illinois. It's actually, the Farm Progress Show is one of the largest outdoor farm exhibits in the country. It brings about 150,000 people a day to Decatur, Illinois. And Decatur is not prepared to handle that kind of traffic volume, much less so than Urbana is. There's basically one or two major entrances that people use to get to this event, and it creates such bad traffic in Decatur that it actually generates a queue on the freeway that runs on several miles long. And it's a huge safety concern for the highway engineers and for the state of Illinois, because you get semis cruising through there in the morning, most days of the year, not expecting any traffic, and then all of a sudden, one day every 2 years, you have cars that are just completely stopped on the freeway. Huge safety issue. So what we worked with the Macon County Highway Department and IDOT on was using Traffic Turk, measuring throughout the Decatur area, the main routes into the show, where people are coming from and when they're coming here. And then we explored the possibility of actually rerouting some of the traffic during future shows to see that if we could get more people, for example, to get off the freeway here or get off the freeway here, the show is right here, we could actually get rid of some of the vehicles that are being queued up on the freeway and actually dissipate the queue. And if you can have the queues generated on the surface streets, if there's an accident, it's much less likely to generate a fatality than if you have an accident on the freeways. So we just finished up that work and actually demonstrated that with an appropriate rerouting, it actually would be potentially possible to get that queue eliminated off the freeway. Just to give you an idea of what some of the testers look like there. Again, in Decatur, we had another issue that there's major safety concerns, right? It's not like Urbana, Champaign, where there's sidewalks everywhere for people to sit on. In Decatur, the sidewalks aren't there, so we had to make sure that our counters were visible. We worked with the county highway engineer to actually go and identify safe spaces in the field that users could count from. And we worked with all the local police officers who were directing traffic during those events to make sure that they also knew, don't stop and mess with this person. They're part of the experiment. They're supposed to be here. Their car's not broken down. So again, we're learning an awful lot about how to actually manage realistic issues with building systems that are not just sort of like, oh, Facebook crashed or Twitter went down again. I mean, everybody remembers the fail whale, right? You can't do the fail whale during an event. You've got one shot to get it right, and if you screw it up, somebody's life could be on the line. So that really puts a much higher bar for sort of the engineering excellence that has to take place when you build these systems, because it is so critical that they work and work reliably. So I want to kind of spend a few minutes and talk about, the data comes in, how do we actually process this data, and what are some of the engineering challenges we faced with building this system. The first is just sort of a video of replaying what type of traffic data we get. Again, from these swipes, all we know is that a car went through the intersection and went straight, left, or right as a function of time. Okay? And one of the things that we'd like to know from a traffic prediction standpoint is we'd like to know basically, was there no car moving through here because the light was red? Or was there no car moving here because there just weren't any cars here? And from the non-existence of a maneuver, you can't tell. Okay, so what we actually try to do is we try to understand, in the transportation and engineering community, a phase is basically, you can think of like letting all the north-south traffic move together. And then the next phase is all the east-west traffic move together. Another phase might be left turns that are allowed to move. Okay, so any set of movements that happen through the intersection that last for some period of time, that's a traffic signal phase. What we'd like to do is estimate that from the Traffic Turk data. Part of the reason we can't just get that directly from the traffic signal controllers is because a lot of times it's humans out in the field that are actually doing the traffic control. So it doesn't obey any of the existing sort of engineering guidelines that you might expect if you just went to the city and asked them, how does this traffic signal work? So we use a bunch of statistical tools. I'm not going to spend much time on that, but the main idea to sort of set the stage for how the problem looks, these are some common traffic signal phases. There's 8 different phases for this 4-way intersection. And if you throw in all the right turns, these are all the markers in orange, you can start to see why this is a non-trivial problem. So great, now you saw a right turn happen. And did a right turn, was it on red here? Was it a right turn that was protected, meaning there's no conflicting traffic? There's another right turn in this one, and here, and here, and here, and oh wait, a right turn shows up in every single phase. So a right turn is actually very useless in terms of visually trying to inspect what phase might be happening. So instead what we developed was a statistical tool that tries to look at not only what maneuver is happening, but what maneuvers are happening immediately behind me and what maneuvers are happening immediately in front of me. We use this history of the maneuvers to try to identify that this collection belongs to phase 5, for example. And so just to kind of give you an idea of what the data visualization looks like, on the left, this y-axis here is just labels of different maneuvers. So EBL stands for like an eastbound left-turning vehicle. SBR is a southbound right-turning vehicle. And this is the time series of the data that we collected at Neil and Kirby. Okay, and if you look at this, again, I can't, when you see some southbound maneuvers, you see some northbound maneuvers, it's clear like north and southbound traffic is going here. But I couldn't reliably tell you that almost every single phase at that intersection is present in that picture without some kind of tool to do it. So we developed a hidden Markov modeling framework that actually allows us to estimate the phases from the data. And the green boxes illustrate actually our estimate of what the phase was. We took another person out there to validate what was actually happening on the traffic light. And you can actually see we recover the correct estimate of what the phase was for every one of those swipes that we collected, except for one. And the difference between phase 3 and phase 2, they both have some overlapping maneuvers where you just can't distinguish an allowed left turn from one phase and an allowed left turn from the next phase if they're right next to each other and the last movement is a left turn. So this algorithm actually works surprisingly well, and that's sort of the first pre-processing step we do. We turn all those maneuvers into phases on the server to estimate what's happening at the traffic light. Then the next step, we take those phases, we know whether the light's red or green, and we know how it evolves, but the real question is, how will it evolve in the future? And to do that prediction problem, we need to know something about the logic of how the traffic signal control is operating. Okay? And it can be that it's a traffic light with a control algorithm sitting on the side to dictate based on sensors whether or not the light should change. But again, like I said, in events, this is a picture in Chicago. They have a traffic management aid that literally for special events goes out and hand directs the traffic. I still need to be able to predict what that person is going to do as the traffic conditions change. If I want to be able to say, I see this traffic stream coming in to the event, I know there's a person here who doesn't have very much traffic right now, but very quickly, in the next 10 minutes, they're going to face a huge queue of cars coming at them. How are they going to respond to that? I need to know the logic that they have. You can't ask a person how you control traffic. You have to estimate it from the data. So we actually started working on some algorithms using a branch of optimization called inverse optimal control. And inverse optimal control is really find the control objective that somebody must be doing in order for what they're doing to be optimal. So again, I know what you're doing. I hypothesize or I argue that what you're doing must be optimal in some sense. What is that sense? That's how we sort of recover the behavior that the person has. Okay, so we did some experiments in the field. The algorithm actually works pretty well. We were able to identify out of a suite of different objectives that they might be optimizing over. Feature 11 basically is something that says you're going to minimize the variance of the phase length. In English, that basically means that you're going to try to run this thing like a fixed time. Independent of the traffic conditions, no matter what, every 45 seconds change the light. Okay, that's a relatively easy one to do. For this particular intersection, we're able to recover that that's actually the behavior. It's a little bit trickier with the humans because sometimes they switch, their predictability becomes very difficult. We're working right now on some algorithms that are better suited for humans and not just the traffic signal controllers. But it's at least our preliminary work experimentally for all the signals that we have access to is performing quite well. Okay, on the back end, you saw that the phone produces information about what intersection you're at. The street names don't come from Google, right? Google, the API won't tell you what intersection you're at. So instead, what we had to do was actually build a huge back-end infrastructure that builds our own map, and that map then allows us to geocode all the data as it's coming in, run our traffic estimation algorithms on the network, and then process that back out to the users. So the way that it works is just a basic client-server architecture. All the devices authenticate with the server. We've got a database that stores all of our traffic data, also stores all the mapping information. The map is a huge ordeal. Anybody who's worked with maps knows that basically you can either, if you need the raw geometry, you need the actual lengths of the streets, you need the speed limits, you can't get this from Google. You can buy it from commercial maps. It's very expensive. Or you can use open source data sets. The open source data sets are great, except for the fact that they're not very accurate. So we've been using OpenStreetMap. It is an open source data set. What's really great about it is it has a bunch of tools that allow you to manually fix bugs in the map, and then it'll kick out a new version of the map. Well, that's great, except for the fact that now the map is changing every day, which means that as we get more and more data coming in, we have to decide whether or not we want to keep our incorrect map and dump all the data down into it, or whether we want to constantly keep changing the map, and then we have to figure out how to roll over the data that we collected on the old, possibly incorrect map to the new map. Right? And this is a problem that every major company that's doing any kind of traffic work has to deal with. The map is changing. We find bugs in the map. The road network, I mean, there are construction projects, it changes. So what we did, I mean, some of the work that we do is just pretty standard stuff. We have to do a lot of pre-processing on the map just to reduce the size of the map, also to get rid of a lot of information that's in the OpenStreetMap that we don't take advantage of, like walking paths, for example, very detailed geometry about how many, I don't know, like if there's a curvature to the road or something like that. We don't need it. We just need the length, and we need to know the intersections. So we basically compress all of the detailed map into a much sparser representation, much better because we have to send a whole lot less bits to the phone to actually do any information processing on it. We keep all the detailed information still on the server, though, so that if we want to visualize our results, we get a map that looks like what the actual road network is. Okay, so the main challenge there is, though, now we have a constantly changing map. Our database, what we actually do is we keep all versions of the map. We actually version our map, and data comes in to a specific version of the map. So every time that if you change one aspect of the map, every single element in that map constantly is getting new version numbers to basically account for the fact that some changes happen somewhere in the map. And then we have another consistency problem to make sure that the app has the same version of the map that is the latest version in our device or in our server. And again, this is a challenge because you might not have connectivity with the server. So we have all kinds of additional logic to guarantee that if you collect the data on the map, we have a way to get it back to the map that was in our server that was the most current version. So I kind of want to just give a little bit of an example of what this type of issue is. So update 1, we basically dump down a simple map. Here are all the intersections numbered and all the links between them, just the lines that connect. Okay, and somebody comes in and realizes, there's been a mistake. This node 3 or intersection 3 is in the wrong place. So literally they just move the latitude, longitude coordinates of the map and move it. Well, you move the map, the intersection, but you also had to modify all of the links. Okay, so now we actually get a new change set. So if you query our database at the initial time, you'll see all the original nodes and links. And if you query our database at a later time, you say, what did the map look like at, I don't know, Tuesday, 10 o'clock p.m., and that's after the change has been made, you'll get the new version of the map. So when the app asks for, hey, give me some information about the geometry around me, it's always getting the most current version, and then it will store the data on this version of the map. The old data, when you query the data, it actually tells you, since all the data comes in with a timestamp as well, it tells you it came from the map as it existed at this time as well. Okay, and we can keep populating the things. If you add additional features to the map, which we are doing. We don't have right now the entire world map loaded, but we're constantly adding different areas for different experiments. You want to add that new information. That doesn't really change anything. It just keeps growing the map. Okay? And then the main challenge is, well, if you stored the global map, it'd be 400 gigabytes of data. And then if you're constantly going to store all the change logs for the map, every time somebody puts in new information, the size of the information that you're collecting just grows and grows and grows and grows. And all we're trying to do is make sure that other users in, let's say, Minnesota or in California or in New York, other transportation engineers can use our device. Well, we've got to solve a problem. Either we load up all the data for them, or we have to basically tell them that we don't have the data in their area. The app doesn't work. So instead what we did is something, I don't know how many people are familiar with Mailbox. Mailbox had it's a clever mail application for your phone. They came up with something really good. They basically couldn't handle the load of all the people that were requesting their app. And what they said is, sorry, it's not that we don't like you. We're just too cool for you right now. So get in line for the queue. You're number 400,000. And when we have space for you, we'll let you participate. And in the meantime, that gives them time to actually get the rest of their equipment up and still provide good service to the users that are working. So we did the same thing. We said, okay, well, if you open up the app in a place that we don't have the map loaded, you enter a virtual queue. You're the only one in it, obviously. But what that does is allows us to go talk to OpenStreetMap and grab a huge piece of the map, within, I don't know, maybe 10 or 15 miles of where that person is, load that up in our database, do all this pre-processing on the map. This takes about 15 minutes to 20 minutes, depending on how dense the map is. We don't want our user to be sitting there waiting with a dead app, looking at it and saying, okay, this thing isn't functional because the map hasn't loaded. So instead, we just tell them, we'll alert you when your space in the queue has been, called, and now you can have access to the app. So it just gives us a little bit more buffer time. The user doesn't need to know why we can't let them use the app today. In the background, it lets our algorithms run. When we're sure it's correct, then we can let them have access to the app. And it's just sort of a perception control. There's nothing hard about it, but it's a very clever way of just sort of avoiding trying to deal with users in a partially functional app. Okay, so the main things that I talked about today and some of the work that we're ongoing, I tried to give you a big picture overview of some of the work that is taking place with smartphones and transportation systems. And smartphones and smart transportation systems, I think, will be just increasingly coupled together. I talked about what people are doing today, and I tried to make the case that there are some problems that Google and Apple can't solve, and we designed Traffic Turk specifically to help get temporary sensors in the field quickly to collect the data that you need that nobody else has access to. And I gave you a little bit of a hint of some of the algorithms that we use in the back end to do the pre-processing. Obviously, there's a big team of us that are working on this project right now. I have several grad students that are working on everything from one problem: if the central server doesn't exist and you want to be doing traffic estimates, you can actually have the phones locally talk to each other, and they can run these big network-wide estimation algorithms in a distributed way using a bunch of advanced filtering techniques so that they still get the right answer, but nobody actually has to have perfect global information. And it also makes sure that if the server goes down or somebody else, the phone shuts down, you can still get information from everybody else. We're also working on this sort of estimation of the human-based traffic signal controllers. When the guys are out in the field doing the hand waving, we still need to know what they do. We can do the fixed infrastructure, but getting good models of human behavior is an ongoing challenge that we're working on. And then also we're looking at what happens when you network all this stuff together. If you've got people that are out there controlling traffic and you have real-time information going to those people, maybe you could actually have the police officers manage the traffic in a way that would not just give them local information about what they can see, but information from the neighboring intersections that they can't see, but definitely influences the traffic at what they're doing. So if we can network the controls together, actually the phone would allow us to work better than many of the traffic signal systems in the country. So that's kind of a big picture overview of what we're working on right now with Traffic Turk. I'd be happy to take any questions that you have, and our website also has some additional information if you want some of the technical details with some of the things I mentioned today. So thank you for your time, and I'd be happy to take any questions. There's a question in the back.
Have you, as Traffic Turk, been involved in studies or analysis on North Prospect area, the shopping area?
No, but we would love to, especially if anybody wanted to help finance our deployment there. Yeah, I mean, so this gives you the big picture, right? Those intersections on North Prospect are being reevaluated to try to optimize the traffic signals. And the way that it's done today, you take one person with one of those turning movement counters, they go out to that intersection and they look at the traffic at that intersection, get all the data. They go back the next day and they look at the next intersection, get the traffic data, and then the next intersection. And so the data, I mean, is from 3 different events. There's no way that these conditions, I mean, they're physically connected, but the data is disconnected. So just by taking a couple phones and sending people at all 3 intersections or all 5 intersections simultaneously, you could actually record network performance instead of individual intersection performance. And that's just something that currently isn't done by any agency for managing traffic signals, but I think that's part of why we're putting all these devices out in the field and open sourcing the code and making the app free to download, is because obviously it's trivial to extend it for network-wide monitoring, and it would actually improve the quality of the algorithms that could be used to optimize the signals. Yeah.
Can you use computer vision systems to make small portable things that don't rely on the human factor? Like I can go strap up 6 or 7 of these at different intersections on existing utility poles and monitor things for a day.
Yeah, so the vision is actually an important aspect. There's a couple challenges with the vision-based systems. The first is that for these brief events, you're going to actually spend more time and money doing the installation and the teardown of those sensors, then you calibrating them, making sure that they have the right field of view, than you would just by going out and sending a few people out there. If you're going to be monitoring something for more than a few hours, though, it's clear you're not going to be putting humans out there to do the counting the whole time. So I think depending on what the application is, there's a trade-off between whether vision systems are going to work better or some kind of other sort of more temporary system would work. And then the second piece is that the challenge with the vision-based systems is that you have to have quite a few cameras, right? You might have to have a camera for every different direction of the traffic stream, where we basically cheated essentially by having people do it because they've got cameras that work really well, right? And it's also on a rotation. So again, very cheaply we can get the data. It's really like a cost argument. But again, depending on the application, it's clear that vision is much more reliable for longer periods of time. And you'll see some of the signals around town already actually have cameras mounted on them. And they do that right now, vision-based detection of the traffic systems.
So they're actually pulling.
Yeah. The challenge with a lot of those systems are that basically that data never gets sent anywhere, because it's been historically very expensive to transmit any information. They stay locally in the box, and then they just get flushed. So there's no way to, there's another colleague I have at Minnesota who's working just on putting in smarter wireless communications devices in the cabinet so that it can stream the data back to servers, so they can get the information that the systems are already collecting just back to people to use it. So again, depending on the application, I think this is by no means the solution to all the problems. It's just for some problems, it really helps us very quickly get the data. Okay, so there and there, yeah.
Are you using the data that you've collected through Traffic Turk for any real-world planning, or is it more of an academic exercise at this point?
Yeah, so this experiment in Decatur, the Farm Progress Show, that was actually the point, was to try to help the county collect the data they need to assess whether or not rerouting the traffic is even remotely possible. And then so we did some preliminary analysis to say, actually, yeah, based on the traffic we saw at this event in 2013, if you did this kind of reroute, and if you could get this many people to actually follow the rerouting advice, and if you had people managing the traffic lights to manage this additional flow, it would be possible to get the traffic off of the freeway. Of course, that's, as you mentioned, you can see, if, because you go out and try it the next time, it could be a different event, it could be different traffic patterns, and it may or may not work. But that was really the goal, is to actually try to make this stuff not just academic in the sense, now we got the data, what can we do with it, but really actually try to solve practical problems that the cities face. So
a year and a half from now, they may implement some of your suggestions, or?
I'll leave them. I would like that to happen. It's obviously more complicated than what I've led you to believe, because there's another issue with the fact that when you reroute traffic, you're taking it off of a highway managed from IDOT onto city streets, which were managed by a different municipality. And so there's lots of coordination and things like this that have to go into making any of this traffic control on special events work. So there may be other reasons why it may or may not actually work in practice. That's part of our work with the county, is to see, now that it's technically feasible, what other challenges are there?
Yeah. Stepping aside from the civil aspect of this project that you're doing, do you see it essentially running as far as an SDK being implemented into corporations, things like that handles? Because for my business, I handle on-demand drop shipping ability, and in the recent Uber, they had a lot of flack in regards to their algorithm doing search pricing.
Yeah.
So do you see traffic curve being something?
Yeah, let me say that I'm an academic, so we build tools that allow us to do research, and then we're not trying to start companies off of this stuff. However, we want to see the stuff work in practice. So I don't think that, personally, I don't think my lab has the resources to actually build out a full SDK for this and manage all the users and things like this. But I think as a general principle of being a public university, the data and the code should be available. And so we're right now working with trying to make sure that our server can't be trivially hacked because of all of the source code that we've dumped out there. But at the same time, I expect within the next few months we'll have all of the source code for our entire system dumped out there. And then if somebody, then anybody can look at it. If they want to take the time to actually do something with it, then we're more than happy to support them in whatever they want to do. But short of doing an SDK, I think the next best thing we can do is just make sure all of the content that we did, all the engineering effort, all the problems that we solved is actually out there so people can see what we did, how we did it, and change it if they want to support their own needs. Yeah.
Mine's a more trivial question, but just do the monitors do only one road in both directions, or do they do the entire intersection with all 4 movements?
They do, yeah, they do all directions, all movements. And you can imagine that something like Kirby and Neal during a football game, there's a tremendous amount of traffic that goes through there.
So your target monitor is like a 14-year-old boy then, right?
Well, so yeah, this comes to an interesting point. In our volunteer form, we actually ask people what their favorite iPhone or Android game is, right? And that's sort of like a quick sanity check. If you don't play any games on your phone, we're not going to assign you to the heaviest flow traffic intersection. Yeah, exactly. So that was one of that was one of the options. But it's true. Like, hand-eye coordination or finger-eye coordination is important for those very high-flow intersections, especially if it's the first time you've done it. But I can tell you that the different demographics between Decatur, the volunteers we had from the local community there, compared to the students that we recruited in Urbana, compared to the students that we recruited in New York. I mean, we've seen a wide variety. I think the age range of users we've dealt with is anything from probably 8 years old at the engineering open house to just short of 80 years old at another event. So this becomes part of why the UI and everything else becomes really important. Okay, well, thank you again for all the questions, and I hope you enjoyed the talk, and I'll be around for a few more minutes outside if you have any additional questions. So thank you for your attention, and I hope you enjoy the rest of the event.